Now let's learn a few more definitions having to do with these undirected graphs. We're going to be talking about walks, trails, circuits, paths, and cycles. So we're going to start with a walk. That's the most basic of these. So a walk from V0 to V1 in an undirected graph G is a sequence of alternating vertices and edges that starts and ends with a vertex. So basically we're going to start at a vertex, walk along the edges, and get to new vertices. Okay, so anytime we start at a vertex and use an edge to walk along it, get to another vertex, then we can use another edge to get to another vertex, and so on. And if we come up with a little sequence like that, that would be called a walk. It's like we're walking along this graph from vertex to vertex, always on an edge. Okay, so that's officially how we could define or denote a particular walk. We could notice there's some kind of strange brackets around here. There's a less than bracket. Well, it's not exactly a less than sign. It's kind of a wider less than sign. That's on the left of this sequence, and then we have a greater than, one that looks kind of like a greater than on the right hand side. So we'll put the walk inside these brackets that look like that. And so you see what they have. They list a vertex, list the edge that we need to walk on, and then the new vertex where we're at, and then the edge that we walk on past that vertex to the new one, and so on. So it would be vertex, edge, vertex, edge, vertex, edge. That would show where we're walking along this graph. Okay, and this says the vertices just before and after each edge are the two endpoints of that edge. So, we're not going to try to walk from A to B on that edge and then end up somewhere else. We're always just going to walk from one vertex to the other side of that edge, right? Okay, so that is one way that we could denote a walk. But we have a simpler way by just leaving out those edges, but just mentioning the vertices, okay? Because the edges are completely determined by the vertices, right? The understanding is if I go from V0 to V1, I walked along that edge, V0, V1. So we can just leave out the edges and just mention the vertices, and that can tell us where we went on our walk. Okay, so here we might see, and I'm going to just use this standard less than, greater than symbols because that's all I have on my computer. So anyway, B, H, G, E. That would be like starting at B, walking to H, walking to G, walking to E. You see that there's lines where I would want to go there. So that would work. That would be a walk. Let's look at another one, A, D, F, I. So going from A to D to F to I, that's a walk because I've walked through those vertices and I've used the existing edges. Now FIB, that is not a walk, and the reason why is because there's not an edge between the I and the B, right? So I could go from F to I on an edge, but I can't get from I to B. There's no line there. So that would not be a walk. I'd have to go to E first, right, before I got to B. So F-I-E-B, that would be a walk, but F-I-B is not. So let's take a look at the same graph and see if we can find which of these, A, B, or C, is not a walk. So I'd look at E-I-F-D. So can I go from E-I-F-D? Yeah, I could draw a lines, going, draw over the edges to see, and yeah, I could go from E to I, I to F, F to D. There's edges there. So yes, that would work. B to H to B. Okay, there's an edge between B and H. That's fine. But what about A, D, I, C? I could go from A to D, but I can't go from D to I, right? There's not an edge between D and I. So that is not a walk. The length of a walk is the number of edges in the walk. So the length of walk DFIEG, let's first determine it is a walk. We can go from D to F, F to I to E, E to G. So how many edges did we walk on there? Well, we went from D to F, F to I to E, I to G. So there were 4 edges we walked on. So we'd say the length of that walk is 4. Now, it's possible to have this just one vertex in there, and it's like we started somewhere, we started at a vertex and didn't go anywhere. So that would still be considered a walk. It's just that it's considered a walk of length 0. Now there's what we can call an open walk and a closed walk. An open walk is a walk in which the first and last vertices are not the same. So you end up in a different spot than you started. But a closed walk is a walk where the first and last vertices are the same. So I start on some vertex and I walk around and I end up back where I started. That would be a closed walk. So which of these would be a closed walk? Well, all we have to do, assuming that we don't have to verify that they're both walks, and we'll just assume that, and that might not be something you can't assume, but in this case here, these would be valid walks. So if that's the case, which of these would be a closed walk? Well, that'd be pretty easy to tell. We would just say, well, the last one starts at B, ends at B, so that would be the closed walk. First one does not end where it started, so that would be the open walk. Now, let's talk about what is a trail. A trail is an open walk in which no edges occur more than once. And think about a trail in real life. A trail, goes past certain, maybe you could say little checkpoints or whatever. A trail, if we call something a trail, we would not ever, there would never be any retracing of steps. That wouldn't make the trail. You wouldn't say, I'm going to go along this trail, and you get to one point and it says, well, go back to where you were before, and then go a different way. That would be a weird trail, right? So anyway, so that's why, I'm just trying to kind of correspond what we know as a trail in real life to this to kind of help you remember. So a trail, it's an open walk. You're not going to end up back where you started, but no edge occurs more than once. You're just going along a trail. You're not going to retrace any steps or go over an area more than once. So FIEGH. See where that goes? That is a trail. Starts at F, goes to H. It's a walk, right? Because it has to be a walk before it can even be considered a trail. And it's a walk because there were edges there. And it's an open walk, but no edge occurred more than once, so we would call that a trail. This, however, is not a trail. FICIE. That's a walk because I can walk that F to I to C, C to I to E, but it's not a trail, right? Because that edge IC occurred more than once. We would have been walking on that edge more than once, so we would not consider that a trail. A circuit is a closed walk in which no edge occurs more than once. Okay, so the circuit is like a trail in that there's no edges that occur more than once. But if it's a closed walk, then we wouldn't call it a trail, we'd call it a circuit. So AEBA, that would be a circuit because it's a walk, it's a closed walk, and no edge occurs more than once. This one here, going from D to A to E, back to A, back to D. Okay, that is a walk, and that would be kind of a walk that we might do if we're taking a walk around the neighborhood. Start at home, go, a couple places, and then retrace our steps. And we ended up where we started, but we were retracing our steps. These edges occurred more than once, so that would not be considered a circuit. It's a closed walk, but not a circuit. Okay, we keep adding on these definitions. Here's a path. What's a path? A path is a trail, and remember, for it to be a trail, it has to be an open walk where edges don't appear more than once. A path is a trail in which no vertex occurs more than once. So let's look at some examples here. F, B, A, C, B, I. That would be a trail, right? Because it's an open walk, and we're not walking over any edge more than once, right? F to B, B to A, A to C, C to B, B to I. So that would be considered a trail, but it's not considered a path, right? And the reason why is because B was in there twice. You would be visiting the same vertex more than once there. And I guess if you think about what path means to us, that does kind of make sense. A path wouldn't go back to where you've already been. Now, a cycle is a circuit. So if it's a circuit, remember what a circuit has to be. It's a closed walk where no edges appear more than once. But if it's also, and if it's a circuit with length at least 1, and that's, we have to realize we can't just be staying on one vertex the whole time. We got to have some length to it for it to be able to be a cycle. A circuit of length at least 1, in which no vertex occurs more than once, would be called a cycle. But now, of course, the first and last vertices have to appear, together, because it wouldn't be a closed walk if they weren't. So we're saying except the first and last vertices, which will always be the same. So we'll always see the first and last be in there and be the same vertex, but anything in between, the vertices can't be repeated. So FBIF, take a look at that. We would say that is a cycle because it's a circuit. It's a circuit because it's a walk, closed walk with no edges happening more than once, but also no vertex occurs more than once. So we would call that a cycle. But this is a cycle, this is a circuit that would not be considered a cycle. So let's take a look. Start at F, go to B, go to A, to C, to B, to I, back to F. So it's a closed walk, and it's a circuit because we didn't walk on any edge more than once. But it's not a cycle because we did have a vertex that showed up there twice. The B was in there twice. Now, of course, again, the F is in there twice, but it's okay if the first and the last are the same. That's what's going to make it a closed walk. So, you could be, if I just gave you this FBACBIF, this last one here, and said, is it a cycle? You would be looking to see if any vertices appeared more than once, and it does. So then you'd say, no, it can't be a cycle. Now, it's kind of helpful, I think, to come up with a little diagram to kind of help us make sense of all of this. because we have a lot of these new terms, and we can get confused between a trail and a path and a circuit and a cycle. So what I've come up with is a little diagram here that might help us, and you might want to have that available when you're doing your activities so that you can keep all of this straight. So let's start at the top. We all know what a walk is. Now, but of all of the different types of walks, we could have either an open walk or a closed walk, right? So let's go to the side of open walk. So let's say we've got an open walk. Well, now, all open walks are walks, right? Looking at that, going back and forth between this arrow. All open walks are walks, but not all walks are open walks. So as we go from walk to open walk, we're getting more specific, okay? Now, if we start with an open walk, we can get more specific and go to a trail. All open walks, no, all trails are open walks, but not all open walks are trails. And then we can go from trail to path. All paths are trails, but not all trails are paths. And we can do the same thing for closed walks. So we can go from closed walk, we would go to a circuit, and then get even more specific and get to cycle. So, we're getting more specific as we follow along those arrows. And, along the horizontal levels, we kind of see that we've got some corresponding things. The trail and the circuit are alike in that there's no repeated edges. And then the path and the cycle are alike because there's no repeated vertices. So anyway, just kind of having that handy to look at might kind of help you in making sense of all of this. Now, I've got an exercise that is there in zyBooks at the end. It's one of the additional exercises, the number 1 from this section. I've gone ahead and put it up here, and we're going to kind of look at them together here and see if we can find these answers just by getting a little bit of practice here together. But what I want you to do also is I've opened up the solutions for that particular exercise, and I want you to go and do it over on your own if you want some more practice. I think you're going to get practice anyway with your regular participation activities, but just in case, if you want more practice, come back and do this one again too. Okay, so this says the sequences given below. Some of the instructions are covered, but basically they're showing all of these things that we've learned that are new, and they're asking us for each of these, A through G, what are they? What of these are they? So this first one, A, B, C, D, A, C. Well, first of all, is it an open walk or a closed walk? Well, it's an open walk because it doesn't end up where it started, right? So we'd say it's an open walk. Is it a trail? And so the trail would be next. Well, the trail can only be if we haven't repeated any edges, right? Let's see, A to B, B to C, C to D, D to A to C. Did we have any edge repeated? No, we didn't really. And it might be kind of hard to see. If you want to, you could actually put some vertices, out there on your paper and look at it that way too. We did, though, have A appear twice, right? So A appeared twice, not as the first and last, because A was the second to the last. So we had a vertex appear twice, but there is no edge. And I kind of had to think about that a minute. You kind of think, because I did go back to A, but did I go did I go over the same edge twice? And it turns out we didn't. So we would say it's an open walk, and it is a trail because no edge is repeated. But because A appears twice, not at the beginning and end, but beginning and next to the end, then we could say it's not a path. Okay, B, A, B, C, D, B, A. Well, we would say it's a closed walk because it starts at the same place as it ends. So it's a closed walk. Is it a circuit? It's a circuit if there are no repeated edges. Well, this one's pretty easy to see. To get from A to B, I'd walk on that edge, but then I also have to go back from B to A at the end. So that edge, AB, I'm walking on more than once. So it's a closed walk, but it doesn't even make it to the category of circuit since the edge AB occurs twice. And you could say, well, what about, trying to look at the definition of cycle? But remember, a cycle is a circuit that has even more specifications. So if it's not a circuit, there's no way it's going to be a cycle. So you don't even have to think through that. If it's not a circle, it won't be a cycle. Okay, the third one, A, C, D, E, B, A. So that's a closed walk. Do we see any repeated edges? I don't think I do. Do we see any repeated vertices? We don't see that other than the first and the last. So it's a closed walk and it's a circuit since no edge occurs twice and no vertices are repeated except for the beginning and end, so we would also say it's a cycle. Okay, let's go to D. A, C, D, E, C, B, A. So it's a closed walk. I see some vertex listed more than once, but first of all, we don't want to go there yet. We want to see what about the edges. So AC, CD, EC, CB, BA. I don't think. Let's see here. Yeah, no edge appears twice. You kind of have to, look at it for a minute because remember that, the vertices might be reversed, like in B, the example B. A, B, and then BA was at the end. So, you're not just looking for something that matches exactly AB and AB. You're looking for maybe AB and BA. So, that's why you have to kind of look for a minute. But no edge occurs twice. Oh, but I didn't see, I was looking, I didn't see that C was repeated, but I do see now that it is. So since C is repeated, it's not a cycle. Okay, A, C, D, E, B. So it's an open walk. Is it a trail? Yeah, it looks like a trail because it doesn't have any repeated edges. And is it a path? Well, I don't see any repeated vertices either. So it's an open walk, a trail, and also a path. Okay, F, A, B, A. Well, it's a closed walk. Is it a circuit? Well, no, it's not, right? Because we go from A to B and then back to A. We're on that edge twice. So it's not a circuit, and since it's not a circuit, we can't even consider it being a cycle. So we would say that it's a closed walk, and that's all it is. Now G just is this very small walk. We just don't go anywhere. We start at A and we stay there. So that's still considered a walk. Remember, it's a walk of length 0. And is it a closed walk or an open walk? It would be closed because I ended up in the same spot that I started. But then, is it a circuit? Well, this is where you might think, well, I don't know, would that be considered a circuit? I didn't repeat any edges, and maybe it would be a cycle too because I didn't repeat any vertices except for the first and last. But if you go back and look at the definition of circuit, we mentioned when we talked about circuit, a circuit has to be a closed walk with a length of at least 1. and this does not have a length of at least 1. So it doesn't fit the definition of a circuit. So, oh, I'm wrong about that, and I don't want to go through this again. So, the circuit, okay, I was confused. I was thinking it was the circuit that has to be of size 1, but I guess I was wrong, and we can go back and look. I was thinking it was the circuit that had to be length at least 1, but evidently it's a cycle that has to have a length of less than 1. I mean, it has to have a length 1 or greater to be a cycle, but it can be a circuit. Okay, so that's something, you know, kind of arbitrary that we'd have to just remember. And I'm going to go back and verify this because I didn't remember that. But anyway, so I guess the circuit can be of length 0, but a cycle has to have at least a length of 1. So it can't be considered a cycle because its length is less than 1. So we'd say it's a closed walk and a circuit.